Okay. All right, so aluminum trichloride. So as you guys are first practicing this stuff, I recommend figuring out their formal charges, their valence electrons first. So AlCl3 is a group 3 element. So we have 3 plus, and then what about the halogens? What do they bring?
7.
They each bring 7. Okay, so no matter what structure I come up with, we must have exactly this number of valence electrons. So we have 3 times 7, 21, plus 3 is 24. All right. So moving forward in this class, the way I want you guys to approach this is typically things that are in group 3. They typically like to form things that have 3 bonds to them if they have a 0 formal charge. So they tend to do things like this. Do you guys remember any exceptional rules about things in group 3 with their in regards to their octet rule?
They can violate the octet.
They're typically satisfied with only 6 electrons. And that has to do with the fact that they can get a full p subshell with only 6. So you're going to see that aluminum and boron in particular do this. So with that in mind, I already know that I'm going to start off with this, like so. And then if I fill in my halogens, like that. Another thing we're going to see in this class is oftentimes halogens, more often than not, will form a single bond with 3 lone pairs. So the way to get quick at doing these Lewis structures is to start recognizing patterns. So we have this kind of pattern showing up here. We have, group 3 element, aluminum or boron do this. This way they have a 0 formal charge. And then all of the halogens will do this. And what I recommend doing with the number of valence electrons is if you think you have a wrong structure, you can use that to confirm. So if you were to go back through, we see that we have 3 bonds. That's what, 6 electrons. And then we have 9 lone pairs. That's 18 electrons. And 6 plus 18 is 24. So you could do that as a check as you're getting used to this stuff. Does anything here have a non-zero formal charge? No. So we don't actually write the 0 then unless you're being asked to. But if in the case of a non-zero, we just go ahead and don't show it. All right, let's go ahead and wait before we move on here. What shape does this make? It's trigonal planar. What do you guys know about the hybridization here? It's sp2. And does this compound have a pi bond? No. We're going to see later on in the semester if we have this kind of compound here, a trigonal planar sp2 hybrid. Typically, aluminum boron do this. We have a p orbital that's empty that can accept electrons. And that is going to play into how these things react. Whether they're going to donate electrons, accept electrons, all that kind of stuff. So that's why knowing the shapes and the hybridization matters. All right, the next one I want to take a look at is formaldehyde. Formaldehyde. This has the formula of H2CO. So I'm going to try to approach this without counting the valence electrons here. Let me lower that a little bit. There we go. And go by the common bonding scheme that we typically see with these different elements. So with that in mind, which element do you think goes in the middle? Carbon. And why does carbon go in the middle again? It's the furthest down and left on the periodic table, right? So it's further left than oxygen is. So we put it in the middle. So, and you're going to see in this class in general, carbon's going to go in the middle. And then we can just go ahead and arrange the other elements symmetrically around it. Okay, and then we need to connect by at least a single bond, like so. All right, so now I need to figure out a way to put this together such that we have all zero formal charges.
Double bond carbon oxygen.
Yep. So double bond carbon oxygen, and then that's going to put 2 lone pairs on this oxygen. So I am going to make a table here in a few minutes, but I recommend remembering the common formal charges and the kind of bonds, non-bonding, all that kind of stuff that go with each of the main elements that we're going to talk about. So another possibility you could have drawn for this is this one. Like so. Where we end up with a single bond there. And in this case, do we have all zero formal charges now?
No.
What's different about it? So oxygen should be -1. The way you want to show -1 charges is I don't want you guys to actually write out -1 anymore. I want you guys to write a negative symbol and circle it. And I am particular about that. If you write a negative in there without circling it, it's technically incorrect in my eyes. So I want you guys to start circling your charges. And it may seem like I'm being really kind of picky right now, but it'll make sense later on. We have more complex structures. You want the non-zero formal charges to stand out.
Would those two be isomers?
They're not isomers of each other. And then carbon here has a non-zero formal charge. It's going to be +1. Does anybody know the relationship of these two to each other? They're not isomers. They are resonance structures, yes. So the way we show that is we can go ahead and put this arrow in between them, the double-headed arrow. That is the resonance arrow. Okay. Another possibility would be to show I'm going to show the bad Lewis structure here. These are the kind of things that you want to avoid. And I'll go ahead and point out why it's bad. So in this case, what I did was if you're comparing it all to the middle one, I'm basically changing where that lone pair is going. So in this case, I need to put the lone pair on this carbon. And then the charges are going to be a little bit different. What is the charge on this oxygen? Positive. It's positive. And what about carbon? -1. Okay, so when you're doing resonance structures, the main thing that you're doing here is no atoms are moving, only electrons do. But you need to be able to identify what's a good resonance structure, what's a bad resonance structure. I would argue that this is a bad resonance structure for the fact that we have a positive charge on oxygen. That is a standout, but that's not always bad. It's only bad when you have an unfilled octet. So what you want to do is avoid positive on heteroatoms with an unfilled octet. So there are situations in this class where we're going to see positive charges on oxygen, but more commonly the way we're going to see that is where we have 3 bonds and 1 lone pair. So notice how if we draw it this way, this is actually okay because oxygen in both cases here has an octet, where in this one it doesn't. So if you were to draw the one on the left, this would probably be my response to it, is the red X through it. It is not correct. Okay. See if you guys remember any resonance rules from freshman chemistry. Do you guys know which one is going to be the major contributor of them? Which one will be the major form that this compound takes? The one that has the double bond. So in general, if you're looking for the most stable resonance structure, you want to look for the one that has the most bonds, as well as the one that has the least amount of non-zero formal charges. I'm going to summarize this out in a few minutes. I'm just kind of talking through it here now. Which one would you say is the real structure? So the question I have for you guys, are resonance structures representative of real structures?
No.
No, they are representing a portion of what the structure may look like. The real structure is actually a combination of all the possible resonance structures. And a good analogy I like to think of is some people like to think of a nectarine as being a combination of a peach and a plum, but at no time is a nectarine a plum. It's always a nectarine. Does that make sense? So at any given time, it's a combination of both the features of a nectarine, of a peach and a plum. In case you're not sure which one's which, the nectarine is the one that has the smooth surface, the peach is the one that has the fuzzy surface. So that's why some people say that it's kind of an in-between where the plum is all smooth. But at no time is the nectarine a peach or the plum. It is always a nectarine. And the same kind of thing happening here. So it's always a combination of all the different possibilities. All right. With that in mind, I want to go ahead and just give you some rules for resonance, just so we have them. So resonance rules. You guys are going to be pros at resonance structures before the end of this year. We're going to be doing them a lot, particularly next semester though. All right, so the first rule here is resonance structures only exist on paper. The real structure is a combination of all the different possibilities. So resonance structures only exist on paper. The real structure is a resonance hybrid. Once again, that means that we are basically combining all the different possibilities, and overall, that's the real structure. All right, rule number 2 is probably the most important rule, is you only move electrons. So only move electrons. Because we're not going to be moving any atoms here, in order to prevent from moving atoms, we have a limitation on what you can move. You can only move pi bonds and lone pairs. Pi bonds and lone pairs. If you're trying to show the movement of a sigma bond, the result is the breakage of that bond, which is not a resonance structure, right? All right, and rule number 3. All contributors must be valid. Lewis structures. So I gave you an example of a bad Lewis structure that's not valid. That was the one where you had the oxygen that had the positive charge on there without the filled octet. And all right. So in general, if you're looking at the stability of these, more covalent bonds and less non-zero formal charges is more stable. All right. And also in general, structures that have full octets tend to be more stable as well. So full octet is more stable. All right. There are more rules that technically go with this, but we'll keep it brief for now and then do some examples to help you guys make sense of it all. Oftentimes, if you're practicing your Lewis structures and you see that you have more than one right answer, that's typically the case where you have Lewis or resonance structures as a possibility. And I think the example we did last time was the nitrate ion. You could draw resonance structures for nitrates. But I want to go ahead and take a look at carbon dioxide. And we're going to go ahead and draw some Lewis structures, formal charges, resonance, that kind of stuff. All right, so carbon dioxide is CO2. And without doing the nasty method, I think we could come up with a structure for this. So carbon's going to be in the middle. I'm going to arrange the oxygens on the outside symmetrically. I need to connect them each with at least a single bond. So now, instead of just thinking about the total number of valence electrons here, I want to start thinking about, okay, how can I put this together and get all 0 formal charges, if that's possible? What do you guys think? 2 double bonds, right? That'll make sure everything is 0. So double bond, carbon now has the formal charge of 0. And then what about the oxygens? They should each have 2 sets of non-bonding electrons. If you wanted to, you could go back and count up the valence using the periodic table and then confirm. But I'm trying to step away from that approach because that's just going to be a time sink. Anything that's a time sink you want to avoid because you don't want to waste time on the test and the quiz doing stuff like that. All right, so can you guys think of some possible resonance structure that I could draw for this? So you could have drawn it where the electrons were not symmetrical, right? So an example of that would have been where I had a single bond here and then a triple bond here. Like this. Like so. So that is a valid Lewis structure because we're not violating any of the rules that I mentioned earlier, but we do have some non-zero formal charges. So it looks like this one's going to be -1. We show that as a negative circle. And then what about the other oxygen? So oxygen is group, what's that? +1. All right. So one thing I want to point out here that I did not mention as part of the rules is that the total charge on each structure must be exactly the same. That way you're making sure that you have the same number of electrons in each. So the total charge must remain the same. So, for example, if you're drawing resonance structures there, and you think you may have come up with a bad resonance structure, you can quickly check your work by adding up the formal charges on that structure, and then compare with the previous one that you drew, and see if they match. They should match. If you're doing it correctly, they should match. Another thing too, we'll go ahead and start doing some arrows today, is that the electrons always move from electron rich to electron poor. So electrons move from electron rich to electron poor. And I'm going to add to this or towards a electronegative element. The more electronegative element. All right. So the reason why I'm pointing this out here is because what we're going to be doing this semester is drawing the electron movement. This is something you guys probably did not do last semester. So the way I'm going to show this is this electron is going to go To make sure that we're going from this structure to this one, notice here how we have a new triple bond there, and it looks to me like one of the lone pair electrons is what moved. You guys see that? This one has 2, this one has 1. So the likely case what happened is this moved over. I can't stop there because if I were to stop with that one arrow push, we would end up with 5 bonds to carbon, which we know that can't happen because that'll violate the octet rule on carbon. So to prevent violating the octet rule, something has to give. And that means this will go over like that. And this also lines up with what's happening down here in that we have a single bond now. Okay, so these are the kind of arrows that we like to use. Some people call them like the fishhook arrows or the curved arrows. They're the kind of arrows we use for resonance to show electron movement. And this means that 2 electrons moved. I'm just going to go ahead and put it here now, but we probably won't use this till really later in the semester. But there are a different arrow that shows a half-headed arrow. That means that 1 electron moved. So 1 electron moved or 2 electrons moved. All right. Not center. Let me try to center this camera here. That's better. All right. And you could probably draw a few more resonance structures of that. So let me go ahead and do a more challenging example now. I think this one here. I have a little practice handout here that it's separate from the worksheets. I do have it available on Canvas. I believe it's in the announcements. All right, so for the next example here, okay. So last time we did go over the shorthand, didn't we? So something I want to point out here is oftentimes people will shorthand the lone pair electrons also. And so in that case, what you need to do is you need to think about how many lone pair electrons would there be to have the indicated formal charge. So what I mean by that is, okay, here that has a formal charge of 0 on that oxygen. So how many implied lone pairs are on there? 2 sets of lone pairs. So as we're first starting out, I want you guys to just draw them in for practice. And then what about that carbon over there? So there are 2 things that are being implied there. There's H's being implied there. There's also a lone pair being implied there, right? So the question is, how many lone pairs should that carbon have? It's going to be 1 lone pair, and what about number of H's? 1. I think after this example here, I'll make the little table that I mentioned here. Okay, so in this case here, we have a carbon-oxygen bond, really similar to what we saw with the formaldehyde example. If you have a compound that has the carbon double bond oxygen in there, I recommend starting with that and then moving from there. So what I'm going to show here is, okay, so we have a carbon and an oxygen. Electrons are going to move towards something electron poor or the more electronegative element. So I'm going to show electrons going up this way and not the other way because oxygen is more electronegative. And let's draw the result of that. Your basic structure of the molecule is going to remain the same, so we're not breaking any sigma bonds. We're only going to be moving around pi bonds and lone pairs. So this oxygen now has 3 lone pairs. This one still has a lone pair and negative. All right, I now have some non-zeros in there. Looks like we have a negative on this oxygen, and then we have a positive on the carbon. Like, wait a minute, that was kind of funny. Let's go ahead and double check here. This is overall -1. Here we have -1, -1, +1. Overall -1. We're still okay. So in moving to the next step here, remember we can only move lone pair electrons or pi bonds. So any ideas on what I could do next? We can move the double bond, or you could move the lone pair. You're going to have to show both at some point if you want to get all of the resonance structures. So because you suggested it, let's go ahead and move the double bond first. Like so. And we draw the result of that. So once again here, your basic overall structure is identical. The double bond is now here. We are going to be shuffling the formal charges a little bit. Negative, negative. So in order to make it work out, you need a positive. Where should it go? The bottom left carbon, right? So one thing that I usually think about when I'm moving electrons around, if you see something that has a formal charge of 0 initially, and it's losing electrons via resonance, it's going to have a positive in the next step. Because notice here how this carbon here has 4 bonds to it, 4 bonds to it, all of a sudden it has only 3 bonds. So that means it has a formal charge of +1. It lost a bond. Okay, and I believe we can get one more resonance structure here. And that would be the case where, coming from this one, if this formed a double bond to this carbon here. So I'm going to go ahead and show it do this. And I'm going to push this back, like so. So it looks like we're getting about 4 resonance structures here. Okay, and it looks like my negative goes there. So I'm going to step down right here, and I'm just going to redraw the initial one and ask you guys a few questions about it. Okay. What would be the problem with drawing an arrow like that? What is wrong with that? It's not going to a most electronegative atom. But would it be okay to go ahead and just draw the resonance form of this? So now I want to go ahead and compare these two structures. Is there anything the matter with that? Comparing those two?
The hydrogens on the carbon that you're moving that double bond to.
Yeah, so if you look at this carbon here,